Hello everyone, I'm now going to do a limit of inertia calculation again with an integral. This time I'll be integrating over a cylinder to determine the moment of inertia of a cylinder. I'm actually going to do a thick cylinder. Turns out the exact same result happens if you do a thin cylinder. So I thought I'd tackle the quote unquote harder one. So let me turn it over to my document cam and show you how it's done. I'll show you a way to do it. So if you imagine the cylinder like so, has a radius big R and has a mass M, and maybe it has a thickness given by H, like so. I'll imagine rotating it about its axis of symmetry, like so, which I'm going to call that the X. The y-axis is the axis of symmetry, and the x-axis you see here. So this one I'm actually going to use a volume density. So the volume density should be rho, which is equal to the mass divided by the volume. And I think you all can see that that's pi r squared times h. But the moment of inertia, of course, is I, which equals the integral of r squared dm. So this is one of those cases where I don't want to just, stack up a bunch of disks or something like that and use those as my dm, because that would actually possibly cause the r to vary by quite a bit from one edge of the dm to the other edge of the dm. So what I'll choose instead is a common trick. I'll choose a very thin shell like so, whose radius is r, little r that is, and that's from the center of rotation up to the inside edge. That little radius right there is r. Okay, now this formula may not seem exactly right, but if I call that my dm, then my dm will equal rho dv. And here's the part that I'm saying that might not seem so right. Let me relabel this r again since I've obscured it. That's the radius big R. And of course the radius inside is little r. What I'm going to do is imagine that this is basically a rectangle whose length on the inside edge, of course, is 2 pi r. So that's the length of the rectangle, and the thickness is going to be dr. So I'm going to pretend like I can just multiply 2 pi r times dr and get the volume. Well, once I multiply it by h, of course. So that would actually, the 2 pi r dr should give me the area of the little sort of rectangle. And then if I multiply that by the height, then that should give me the volume. Now, in reality, if I actually cut this rectangle, I'd see that it's actually not a rectangle. It would be shaped like that because the outer part is just slightly longer. Remember, it's 2 pi r along here, but the width right here is dr. So you see it's not exactly correct, but if you actually worked out the math of this, and that would require you to calculate pi r squared for the inner side, and that's what you're going to subtract from it, pi r squared h. And if you calculated the outer part, it would be pi parenthesis r plus dr, close parenthesis, squared times h. And you subtract those two, what you'll see is the only difference is terms of the order of dr squared, or di, or even higher and stuff like that. So we're already taking, by doing an integral, we're already taking the limit as dr approaches infinitesimally small. So you can imagine if dr is infinitesimally small, dr squared is even smaller. So that's why we're allowed to use this formula. I might in a later video show you how that works, but basically now our dm is rho times 2 pi r times h dr. So we should be able to integrate that. Hercules, no. This is going to be equal to, I'm going to pull out all the constants, 2 pi rho h. Those are all my constants. The integral, Hercules, shut up. The integral will be equal to r cubed, because there was an r in the formula for dm, plus the r squared. and that'll be dr, and we're going to integrate from r equals 0 to big R. That's easy enough. 2 pi rho h integral of r cubed is 1/4 r to the 4th, and I evaluate that from 0 to r, which clearly gives me, notice the 1/4 becomes pi over 2 rho h, so the 1/4 with the 2 on top makes that a 2 in the bottom, and I get r to the 4th. But now I need to replace that row, and when I do that, I'll get I is equal to pi over 2 times h. The row is going to be m over pi r squared h, and then of course I got r to the 4th. As you can see here, this pi is going to cancel out with that. All these r squareds are going to cancel out 2 of those, and then of course this h is going to cancel out with this h, so I end up with just 1/2 m r squared, and that's the right formula. Easy peasy. Good day.